will go over the topic of logic synthesis, which involves the automatic creation of a logic circuit from a behavioral Verilog code. So logic synthesis is a design step, which is kind of the first step in the back end of the design flow. And in logic synthesis, you use software called the synthesis tools that will do logic synthesis. The two commonest ones in the industry today are Design Compiler from Synopsys and Genus from Cadence. These software tools, these synthesis tools, will take behavioral Verilog code as an input. They will also take some timing requirements as input in a standard format. So the behavioral code, Verilog behavioral code, also known as RTL, if that behavioral code is for sequential logic, that behavioral code is a requirement. The timing constraints or timing requirements is not, is in principle is optional, but without any timing requirements being specified, there is nothing for the logic synthesis tool to optimize. It can simply create a net list or a logic circuit with no sense of optimization. But if timing requirements are given, then the logic circuit that is generated by the tool will be optimized to meet the timing. So those are the two design inputs that are needed for logic synthesis. Then there is also technology input, which is basically the standard cell library. So the standard cell library is provided in Liberty format. So it's the Liberty. Sorry, I see a spelling mistake here, but the standard cell library, the Liberty files are one of the inputs for logic synthesis. Optionally, the standard cell library's left files will also be given to logic synthesis. And then the logic synthesis tool will use these inputs, the design inputs, which is the behavioral code and the timing requirements, and the technology inputs, which is the standard cell library, Liberty models and left models. It will use those inputs to create then an optimized logic circuit. Okay, the logic circuit will implement the logic in the behavioral code, and it will be optimized to meet the timing requirements. So that's the basic idea of logic synthesis. Why is the Liberty model and the left model required? The Liberty model is a must-have. It's not optional. You have to provide the Liberty files of the standard cell library. The left models, however, are optional. The Liberty files will tell the logic synthesis tool what the functionality of each cell in the standard cell library is, and the delay values are also the delays of all the standard cells will also be in the Liberty file. The Liberty file will typically also have the area of the standard cell of each standard cell. So if the area is there, then you don't need to provide the left. If the area is not there in the Liberty file, then the synthesis tool can also read the left models of the standard cells and determine the area from the left files. And when the logic synthesis tool does optimization, it's optimizing for timing and it's optimizing for area. So the synthesis tool will pick cells from the standard cell library to implement the logic in the behavioral code, but will pick cells in a manner that is optimal. That is to say that the standard cell selected will have the minimum area to meet the timing requirements. Okay. So I would like to introduce the use of logic synthesis by considering a very simple example. And in this example, we have a logic circuit that is very simple as it is as small as a single. It's a one gate logic circuit. In this, the circuit is called cell sense, and its description is as follows. The circuit cell sense has two inputs A and S and one output B. If S is 1, then B is equal to A. If S is 0, then B is equal to inverse of A. So that's the sort of description of the circuit. The Verilog behavioral code that models this description is shown on the right here, and we're using the conditional operator, which is the question mark operator here. So we assign to B the value A if S is 1 and the value inverse of A if S is 0. So you start with a description of what you are trying to design, and then you create a Verilog behavioral code to model that description. If you were to do this manually, what you would do is you would not actually need to write any Verilog code. If you were to design this logic circuit manually, you could just simply put together a truth table. The truth table is shown here, and you can see that whenever S is 0, B is inverse of A, and when S is 1, B is equal to A. That's what the truth table has. And when you see the truth table, it's immediately apparent that this truth table is the truth table for the 2-input XNOR gate. So the logic circuit for this the logic circuit for the behavior we want, for the functionality that we want, is just a simple 2-input XNOR gate. The 2 inputs are A and S, and the output is B. Now, if you were to take the behavioral code that is written here, if you take this behavioral code, then you could use a logic synthesis tool to generate the logic circuit. And you would expect that the synthesis software would create a circuit comprising a single 2-input XNOR gate, and we'll see if that happens. But in principle, you could take this Verilog behavioral code, feed it to the logic synthesis tool, and the logic synthesis tool would produce an output logic circuit using gates from the standard cell library. And if the standard cell library has a 2-input XNOR gate, you would expect the synthesis tool would create a circuit with that 2-input XNOR gate. If the standard cell library did not have a 2-input XNOR gate, then it would implement the function using whatever gates are available. And what you would expect if there was an XNOR gate in the library is for the output of the synthesis tool to look like this: a netlist which has an XNOR gate instantiated in it. Okay. So in other words, if you were to take for synthesis, you would feed it the behavioral code that you can see as an input on the left. You would give it standard cell library as a .lib and left models, and then the output of the synthesis tool, you would expect it to be a gate level netlist or a structural Verilog code that looks like this. So the Verilog on the left is behavioral, the Verilog on the right is structural. The difference is that in the behavioral code, you don't see any standard cells. In the structural Verilog code, you actually see a standard cell instantiated. And if the standard cell library has a 2-input XNOR gate called XNOR2, let's say, and then it would instantiate that.